Let us talk about this problem. We are given a binary matrix. We need to count how many distinct rows it has. Let's see this binary matrix. There are two distinct rows, this one and this one. These two rows are repeating. This row has appeared before. This row also has appeared before because this row is same as this and this row is same as this. So output for this particular matrix is 2. Let's see this input. In this, all the rows are same, so our output is 1. Now please pause this video and try to think of an approach that takes a Boolean matrix as input and returns an integer value, which is count of distinct rows in the input matrix. Let us talk about the naive solution first. In the naive solution, we initialize the result as 0. We traverse through all the rows one by one. We begin from this row, then we go to the next row and then next row and then next row. For every row that we traverse, we check if we have seen this row already. We compare this row with all the previous rows one by one. And if it matches with any of the previous rows, then we do not increment the result. And if it does not match with any of the previous rows that we have seen, then we increment the result. And at the end, we return the result. So we begin with this row. This is the first row. It's not going to match any of the previous rows because there is nothing before it. So we'll have result 1. Then we'll come to this row. This also does not match with any of the previous rows. So we'll increment the result. We will not increment the result for this and for this. So our result is 2. Now what is the time complexity of the solution? Let's say there are m rows and n columns. We are going to traverse through all m rows, and for every row we are going to do big O of mn work to check with all the previous rows that we have visited. That work can be upper bounded by big O of mn. So we are going to do big O of m into mn work, which is big O of m square n. Now please pause this video and think of an approach that works in big O of m into n time. Let us now talk about the efficient solution. The idea is to use trie data structure. Let's consider the solution with this example. We have a matrix with 4 rows and the number of distinct rows in this matrix are 3. This row is distinct, this row is distinct, this row is repeating, this is same as the first row, then this row is distinct. Right? So there are 3 distinct rows in this matrix. In these implementations, the main function which counts distinct rows is count distinct. And then this function, count distinct, is here in C++ and count distinct here in Java. In this function, the first step is to create an empty trie. So we create an empty trie, right? And we have root of this trie. After creating the empty trie, we initialize the result as 0. And after initializing the result as 0, we traverse through all the rows one by one. And for every row, we call this function insert, right? And inside this insert function, what we do is we try to insert this row as a word in the trie if it does not exist already. And this insert function does 2 things. If it does not exist already, then it inserts it and returns true. And if it exists already, then it returns false to indicate that it did not insert anything and this row was already present in the trie. One interesting thing to note in this implementation is we do not have is and field in the trie node here, right? Here and here in Java, right? Why? Because we know that size of every word is same here. What is a word here? Word is a row of a matrix. And all rows have the same size. The number of elements in every row is equal to the number of columns in the matrix. Let's now run this algorithm one by one for this matrix. So we begin with the first row. Inside this loop, we insert the first row 1, 0, 0 using the insert function. And how does this insert function work for 1, 0, 0? It goes through the cell, right? Begins with the cell first of this row. And what it does, it checks, does there exist a child already with this? It does not exist. So it's going to create a child for 1. Now it's going to go through the next row, next cell, and it's going to create a child for this cell also. So it's going to create a child for 0. And it's going to go to the next cell and it's going to create a child for 0, right? And since the child did not exist, flag becomes true and it at the end returns a true flag. Since the true flag is returned, our result becomes 1 from 0. After this row is inserted, our result is now 1. Now we go through the next row, 1, 1, 1. We begin with the first cell of this row. 1 already exists in the trie, so we do not go inside this if condition. Then we go to the next cell and we check that this particular cell 1 does not exist as a child of this node 1, right? So what we do is we create a new node with value 1 and make it a child of this node. And since we went inside this if condition, we also set the flag as true, right? Since 1 does not exist, we are going to create a child for 1 here. So we have traversed this row also and we went inside this condition. So insert is going to return true and our result is now going to become 2. Now we go to the next row, 1, 0, 0. And this time we again call the insert function, and inside the insert function, we never go inside this if condition because 1 exists, then 0 exists, then 0 exists. So we return the flag as false and we do not increment the result. Now we go to the next row, 0, 1, 0. So we call insert for 0, 1, 0 and we see that 0 does not exist. So we go inside this condition and we create a node for 0. Now we traverse to the next cell, we create one more node. We traverse to the next cell, we create one more node, 0. And since this insert function returns true, our result is now going to become 3. And we return 3 as a result. So this is how this trie-based solution works for binary matrix problem. Let us now analyze the time complexity of this solution. This solution requires big O of mn time. We are running a loop for m here. Inside this loop, we are calling this insert function. And this insert function is running a loop for n here. And inside this loop, we are doing some constant amount of work. So the time complexity of the solution is big O of mn. How much auxiliary space this solution requires? In the worst case, we are going to store every cell into the trie. So the upper bound on the auxiliary space required is also big O of mn.